In this video, we'll start to learn kinematics in higher dimensions, and we'll start with 2D kinematics. In 2D, an object can do more complicated motions, and there are several names you probably know about. There's projectile motion, and there's uniform circular motion. So we'll talk about these two different motions in detail. But before we get into these special motions, let's talk about some general 2D motion. Specifically, remember when we talk about 1D motion, so I'm going to write on this side and then we'll compare with this 1D motion. When we talk about these 1D motions, in general, we talk about speeding up and slowing down. Now let's review these speeding up and slowing down concepts, and then we'll start from there. So what is a speeding up? If the velocity direction, let's say there's 1D motion and velocity is this way, is in the same direction as the acceleration. So now let's say acceleration is in the same direction. In fact, let me add the x index so that we know it's a 1D motion. If they're in the same direction, then we say it's a speeding up. So now the next instant, the velocity will have a bigger magnitude compared to the previous instant. And for slowing down, the velocity direction is opposite to the acceleration direction. And that's what we call slowing down in 1D. Now, naturally, we'll ask, do you have similar concepts in 2D motion? The answer is yes. So whenever you study a more complicated motion or complicated object or phenomena, you want to decompose that into some simpler motion or simpler object that we know already. So now we're going to do the same here. We're going to talk about how to reduce this 2D motion into 1D motion. So let's say it's 1D plus 1D. And then we'll talk about from the 1D motions concept, we'll talk about speeding up and slowing down in 1D. Okay, so that will be one of the 1D. And the other 1D here will control the direction of the motion. Since in 1D motion, we don't talk about the change in direction because it's always along the same direction. But in 2D motion, we could have the object's motion changing to another direction, let's say y direction. So that will be controlled by the second 1D motion here. Okay, so now let's look at some general relation between v and a. Let's say the velocity, let's say, is this way. And this direction is not necessarily the x direction. Just some general direction we can draw here. So that's the velocity vector. Now let's say there's a acceleration vector along this direction. Okay, so now the difference from 1D motion is that in 2D motion, now the A and V, they're not in the same direction. A is different from V in terms of the direction. Now, as I said, that we need to decompose it into 1D motions. So let's do this decomposition here. And the decomposition I want to do is that I want to use the V here as a reference direction so that I can decompose A into a component along this direction, and let me call the velocity direction as x-axis, then I will have this ax here, okay? And then the other component of a, we call it ay. Now, since I call this velocity direction x, so I'm going to label this velocity vx. Okay. Now, these two directions motion, they're independent in the sense that the ay will not affect vx. So ay does not affect vx. So that means that when I talk about vx motion here, the change of vx here, I just need to focus on ax, the effect of ax. And according to 1D motion, we already know ax in the same direction as vx. So this object must be speeding up. So I call one of the 1D motion x direction and the other 1D motion y direction. So in the x direction, we have a speeding up. Okay, so that's what we know already. Another question is, what is the effect of this ay? Okay, now ay is in the, if you think about, there's a person here, and this person is facing the velocity direction. Now, this ay direction will be to the right side of this person, right? So ay here will be the right side, points along right side of velocity vx. Okay, so the next instant, this object is going to gain a vy component due to this ay acceleration. So this vy component, if I add it to the x component, vx component, to get the total v, then it will change v to the direction to the right side of the velocity direction, the original velocity direction. So I'm going to draw this vy prime. That will be the velocity at the next instant in the y direction, and the velocity the next instant along the x direction is called vx prime. Now, if I add them up, they give us the total velocity at the next instant. Let's call this v prime. So v prime is to the right side of the original v. So that means that the object in these 2D motion is going to turn to the right. So now we figure out that the y direction will control the direction, the turning direction. In this case here is turning right. And the reason of that is because this ay is to the right side of vx. The original vx. Okay, so now let's summarize this discussion. So the 1D motion, the acceleration, one component in the direction of the velocity, original velocity, will control either is speeding up or slowing down. And the other component perpendicular to the original velocity direction will control whether it's turning right or turning left. Okay, so now let's look at more examples of these velocity and accelerations relation. And let me quickly draw the previous one. That's v, and a is like this. Okay, but we do have other relation. Let's say this is the original v. Now a is this way. Okay, And the third situation will be v is this way, and in fact all the v's will be, in all cases, it will be a reference direction, so we can draw in the same direction as this reference direction, but the a now is to this direction or to that direction. Okay, now we can do the decomposition for all these different cases. The first one we do is this v, this a. I'm going to call this in general. I'm going to call the component parallel to the v. I'm going to call it parallel component, and the component perpendicular to the v. I'm going to call it a perp, and that's the total a decomposition. Again, I'm going to have this a parallel, a perp, and that's the total a. Now here I have, that's the a parallel component, that's the a perpendicular component, and that's the total a. And the last case here, a parallel component is this one, a perpendicular component, and that's the total a. Now in the first case here, we already know it's speeding up plus the objects turning to the right. Turning right. Now the second case here, the parallel component is in the same direction as the velocity v, so we still have speeding up. Okay, but now the direction, the turning direction will be turning to the right. Turning left, sorry. Now the third case here, the parallel component is opposite to the velocity direction, so this object is slowing down. The direction of a perp is to the right side of the velocity, so it's turning right. Now the last case is slowing down and turning left. All right, so now we know this general relation between v and a, and let's look at the one everyday example. Let's say here is an intersection of a street, and that's the line separating, the dashed line separating the two directions of traffic, and there's a car here moving with some velocity originally along this direction, and then it's going to turn right at the intersection, and then car later on will be here. Okay, so let's analyze the these cars v and a relation in this turning. Okay, so usually when we turn to the right, originally we were driving at higher speed, and then you want to slow down first, right, and then turn right, and then later on speed up. Okay, so let's see what kind of a direction we have here. So first we have slowing down. Before the car enters the before the car turning right at this section is slowing down. So the a direction will be slowing down and turning right. So it will be this case here, So that's why we can say the a direction will be somehow this way, slowing down and turning right. Now after this car finish the turn, it will, at this section, this half section, you will speed up, and then still turning to the right. So that will be this case here. So that means that the acceleration compared to the velocity direction will be to the right side. That'll be the A we can draw. Okay. Now let's analyze another turn, another car's motion at this intersection. Okay, so now let's say the car will right here do a left turn. Into this street. So usually when the car is driving at high speed, it will slow down, right? Slow down and do the left turn. And then later on, to finish left turn, it will speed up. So again, let's use the center point here as the point where we determine whether it's slowing down, speeding up. Okay, so the first half of the left turn, the car will slow down, right? So it's slowing down, slows down, and turn left. Okay, so that will be this one, right? So the velocity, the acceleration direction will be to the back side and then to the left side. The velocity is like this, so it's left side, and it'll be this kind of A. A is to the left side and to the back side, pointed back side of the car. Now after you finish the turn, the car will have an acceleration still doing left turn, so it's to the left side and then speeding up, so the velocity and A has a component pointing in the same direction as V. Okay, now in the before the half turn, the car has a component of A pointing in the opposite direction to the V. Okay, so the second part of the turn is the car speeds up and turn left. Okay, so let's talk about the projectile motion. So what is a projectile motion? Projectile motion is the name for an object doing motion under the influence of gravity. And because of gravity, there's an acceleration, right? A due to gravity, which is in the vertical direction. Okay, so now let's say we throw an object up, such as a ball, in a certain direction with some initial velocity. We call it V naught. And then in the vertical direction, because there's a acceleration due to gravity, let's draw its A in this direction. Okay, so A equals the gravity's magnitude is G, and then the specific direction will be determined later when we set up the coordinate system. Okay, but that is the general relation that we talked about in the previous slide. We have velocity in this way, and then A is this way. So we can say the object afterwards will slow down, right? Slow down, and then turn to the right. Okay, now its trajectory will look like this. Look like this. Okay, so that will be the trajectory we can expect from this object's motion. And to analyze this motion in detail, we're going to build a coordinate system. And I'm going to use the horizontal direction as the x-axis. And the vertical direction as the y-axis. The original position of this object, I'm going to use it as the origin O. Okay. All right, so now here is the trajectory. So we want to understand these objects' property, right? Its motion's property. So I want to understand, for example, how high can this object go? So I'm going to list several things that we're going to discuss for this projectile motion, for this special 2D motion. So the height h to the highest point, that would be something that we're interested in calculating. And then the horizontal distance, we call it the range. There is also a quantity that we want to calculate. Okay. Now, in the process of calculating these two quantities, we're going to talk about the time of flight. And that is t total. So what's the total time for this object in air before it falls to the this starting position again? Okay, so we're going to assume that let's say this object started from the ground level and then go down to the same level again later on. And what is the time for that? And we're also going to talk about what's the instant the object reaches this highest point. So let me call this th. So that's the time to the highest point, th. And what is that? Okay. Now the key thing to understand is 2D motion is that the motion in the x direction does not affect the motion in the y direction. And vice versa, the motion in the y direction does not affect the motion in the x direction. So x and y motion are independent. That's the key thing. So that means that I can write down two sets of 1D kinematics. Okay, so now look at x direction first, which is easier. So in the x direction, we know the object has an initial velocity component. So now let's say the original angle here for V naught with respect to the x-axis is theta. Then we can say in the x direction its initial velocity at t equals 0 second instant, the initial velocity x component is V naught cosine theta. Okay, that's the t equals 0 second instant, and we also know its initial position is 0 because it's at the origin. Now its acceleration is always 0, right? So we neglect air resistance. So under gravity only means we neglect air resistance. So that's why ax should be 0. There's no acceleration along the x-axis. Now in the y direction, at t equals 0 second, we have Vy naught equals, so now the y component of the initial velocity is V naught sine theta. Y naught is 0. Ay is So now I can talk about AY, the sign of the acceleration, because now we build the coordinate system to be upward. So A here should be negative g. Okay, so that's why I can add, now I can add the negative sign here and then add the j hat, meaning that the acceleration A here is has only the y component, negative g, and g here of course is 9.8 meters per square second. Okay, so that's the some known conditions for x and y directions. So now let's see, the height h, that's the highest point, should be controlled by the y direction's motion, right? So we know this object here go to the highest point and then turn around, going downward. So this th here is also the turning point in y motion. And the turning point in y motion will mean Vy at this point equals 0 at th instant. Okay, so that will be the condition we're going to write down first to calculate the th. Now in 1D motion for y direction, we have Vy any instant velocity equals Vy naught plus Ay times t. Okay, so now if I specifically apply these to the highest point, then I get 0 here for Vy, and the initial velocity is V naught sine theta, which is positive, right? Because it's the original velocity is y component. Actually, let me draw these components so that we can fully understand its direction. So that's Vy naught, and that's Vx naught. Okay, so Vy naught is in the same direction as y, so that's why it's positive here. And Ay equals negative g, and t at this instant is th. So that's why I can calculate th equals V naught sine theta over g. Okay, so now we already know the th instant is given by this y initial velocity and acceleration g in the y direction. Now we're looking at the object going up from this level and then fall down at the same level. Okay, and this kind of motion is symmetric, right? Symmetric, going to the highest point and then turning back, and then turn back and then go down. So it's symmetric. And you can say that is a special, really special projectile motion, because for some other cases, let's say you throw an object up from above the ground. The ground is not here, it's here. Then you fall to the ground, then you will fall down here, right? Then that will be non-symmetric. Okay, so we only talk about the special case here, symmetric projectile. Now in this case, the second half of the motion will be totally symmetric to the first half. So the total time, or time of flight in the air, will be 2th 2V naught sine theta over g. Okay, so we're going to come back to this condition, to this total time data all. But now let's calculate the highest point y position. Okay, so the general relation for y position as a function of time is y equals y naught plus Vy naught times t, and plus 1/2 Ay t squared. Okay, now if I apply these to the highest point, then I would say this y is h. The original y position is 0, and Vy naught is this V naught sine theta, right? And now we know T here, right, should be replaced by TH, this expression, V naught sine theta over G, okay? And then the last expression here is 1/2 AY. AY, remember, it's negative G. And then the T squared is TH squared. We know sine theta over G squared. Okay? And then we get, now I can actually combine these two terms, right? Because the G squared here will be cancelled by this G, leaving just one G here downstairs. And then upstairs, we know sine theta need to be squared, which will be the same as this term. Okay, so we get 1/2 in the front as a coefficient, and we have 1 here as the coefficient. So that's why the H here equals V naught sine theta squared over 2G. Okay, so that's the height H. Now we know this H here. We solved this. We solved that. Okay, so the last thing we need to solve is the range for this symmetric projectile motion. So in the x direction, at any instant, the x position is given by x naught plus Vx naught times t, and then let's know third term because ax equals 0. So that's why I can say the range R equals x naught is 0. Vx naught is V naught cosine theta. And t here should be t total, which is 2V naught sine theta over G. And that equals, so now I can combine sine theta and cosine theta because there's a, let's put a note here. Due to a trig function 2 sine theta times cosine theta equals sine 2 theta. Okay, so if you know this trig function, then that's good. If not, let's just remember it's an identity from trigonometry. So now if I apply it here, I will get sine 2 theta, and then let's deal V naught squared sine 2 theta, and there's also a G at the denominator. Okay, so that's the range R. Okay, so now we also solve this problem. Okay, so now we know the expression for these parameters. Okay, but let's talk about these expressions. Let's look at in detail what they mean for these objects' motion. So let's first look at the time of flight. What parameters control the time of flight? Or in another word, how can we change the time of flight? The time of flight expression is here. 2V naught sine theta over G. So let me start a new page. So now let's say we fix V naught. Fix the magnitude of the velocity, but we can change its angle. But change theta. Now let's see, G is a constant, so it cannot change the time of flight. So the angle theta can change the total time. Now sine function is maximum when theta equals 90 degree, right? So when it's 90 degree, then we have a total T max, T total max equals 2V naught OG. Okay, so in this case, the object is thrown in a vertical direction. So here's the picture. The velocity direction is this way, and then the acceleration is downward. Okay, and that will be the case here. That gives us the maximum total time in air. Now, what is the minimum time of flight? It's given when theta equals 0 degree. Okay, so now in that case, the minimum time will be 0 seconds. Okay, so that's when we, let's say, throw an object out horizontally, and this object doesn't have a chance to go to the air. It's already in the ground level, at least level. So the total time will be 0 seconds. It's already at the lowest point. All right, so now we finished the time of flight. So now let's talk about the height h. What parameters control this h? And h expression is here. It's this one. V naught sine theta squared over 2g. Okay, let's see. Now we still under talk about h under these conditions, so we can fix V naught but change theta. Okay, so what kind of angle give us a maximum h? Now clearly it's the same situation as the total time. When maximum h is given when theta equals 90 degree. Okay, so in this case, h max equals V naught squared over 2g. And the picture still looks like this one. Okay, now minimum h when theta equals 0 degree. Okay, and the h max will be 0. Okay, so that's the situation here. The velocity, the original velocity, initial velocity will be horizontal, and the object does not have a chance to go in the air. Okay, now let's talk about the third quantity here, the range r. V naught squared times sine 2 theta over g. So the maximum r is achieved when theta equals, now it's 45 degree. Okay, because I have 2 theta here. So in order to get to sine 2 theta equals 1, I need to have theta equals 45 degree. And that's when we have a maximum range, which is V naught squared over g. Okay. Now what's minimum? Minima, again, is given by when theta equals 0 degree. Now in that case, the object is already at the ground level, so it has no chance to go to the air or to travel a certain distance in the horizontal direction. That's why we get 0 here. Okay. All right, so now for this range here, actually has some other properties I want to talk about. So first, let's look at the sine function. So if I look at sine 2 theta as a function of theta angle, And let's draw all possible theta angle. Remember, theta angle is defined as the, let me draw a picture here, as the angle between the initial velocity and the horizontal direction. That's angle theta, okay? And this angle could be 0 here, right? And it could be 45 degrees, it could be 90 degrees. So the range of this angle is between 0 degree and 90 degree. Okay, so that's why I want to draw up to 90 degree. Okay, you don't need to go beyond 90 degree because 90 degrees is the highest point, the largest angle we can get. Now for 45 degree, let me also put a label here. Now if I look at the sine 2 theta, I need to look at 45 degree as the highest value for sine 2 theta, right? Because sine 90 degrees is 1. So I have 1 here. And 0 at both 0 degree and 90 degree. Okay, so that's why the curve looks like this. So it's a sine function. Now if I look at some intermediate value, let's say I'm looking at this point. Okay, suppose this angle, let's say, is 20 degree. Okay, now I will get to some sine 2 theta value equals some value here. But if I extend this line, horizontal dashed line, I will get to the same value here. Okay, now that angle, we can show that is 70 degree. So it's totally symmetric along 45 degree. And if one side is 20 degree, the other side is 75 degree. Okay, or in another word, let's say I label this first angle with alpha angle. The second angle is beta angle. Then alpha plus beta should be 90 degree. And in this case, sine theta, sine alpha equals sine beta. Okay, they have exactly the same value here. So that's why that will give us the same range. So if two angles, if alpha plus beta equals 90 degree, then R for angle alpha will be equal to R for angle beta. Okay, so now for 45 degree, we only have one angle, right? Because the other angle beta will be equal to 45 degree as well as the alpha angle. But for other non-special angles, we always have two different angles that give us the same range. Okay, now some other examples, let's say I'm looking at 10 degree, then 80 degree will be, we have the same range. And 30 degree will be the same as the 60 degree, the range. Okay. All right. So now I want to summarize the projectile motion by drawing some picture. Let's say we have at some instant, t1 instant. Let's say there's a velocity. Let's say along this direction. Let's call this v1. Okay. Now, the next instant, let's say t2, what kind of v should we draw? Okay, so we can first calculate this v2. Remember, v2 is v1 plus a times delta t, and delta t is t2 minus t1. Since we're given these two instants, so we actually know delta t. Okay, and remember a here is its magnitude is g, and it's this way, right? It's this direction. So we actually know a already. Actually, let me draw a longer arrow. That's the a. Now, this delta t is always positive, Okay, so a times delta t will be in the same direction as this vector. So let me draw another arrow to represent a times delta t. Okay, so we're basically looking at the summation of v1, that's this vector, plus a times delta t. Okay, and let me do the head-to-tail method for summing up these two vectors. Okay, so let me copy v1 here, and then a delta t here. Then the summation according to head-to-tail method should be this velocity v2. So we can figure out the velocity direction. And if I want to think about the special property of the projectile motion, I can think about the opposite. Let's say v2 minus v1. Instead of thinking about the summation here, I want to think about the subtraction here. v2 minus v1 is always a delta t, which is always in the downward direction. Which is always downward. So that's why I want to summarize the projectile motion with the following diagram. So let's say we know the original v0 is along this direction, okay? And I want to do, I want to draw the later v2. Let's say the instant here, t1, this represents the instant 0, right? T not instant. The velocity is on this direction. Now how about another instant, let's say t1 instant. So in that case, I should have a times t1 minus t naught, this vector, right, added to the original v naught. So I'm going to add draw a t1 minus t naught here, and then that will give us this velocity in this direction, right? But it should end in this vertical line. So no matter what instant we're looking at, the final velocity is always along this line, and the final velocity starting position is also here. So you should draw, let's say, v1 at instant t1, and its head ends up here. At instant t2, I should draw v2 here. Maybe instant t3, I have v3. Instant 4, I should have v4 here. Okay, so and so on. So let me label all the instants: t2 here, t3 there, t4 here. But in any case, all the later velocities, the velocity at any instant, their head should be here in this vertical line. So that will satisfy the difference between v2 and the initial velocity is in this direction. Okay, that's the a times whatever delta t we have here. Okay, so I hope that summarizes the projectile motion. And that's all. Thanks for watching.